Hello, I'm JBD. I actually currently now working on the instrumentation team at Google. I used to work on the Go team, and recently I was specifically focusing on the diagnostic tools. And today I will talk about distributed systems observability at Google. So first, how many of you have heard about observability? Okay, that's a lot of hands. So since there are many conflicting definitions of this term, I just want to clarify my definition first. What I call observability, or we call observability, is this holistic approach to be able to observe systems for reliability, performance, deployability, and other such properties. We look at multiple different signals in order to achieve that. Metric collection, distributed tracing, profiling, login are a few of those. So this talk is going to be more about the motivation and the concepts we came up in the last almost 10 years to make Google production systems more observable. And I will also briefly what we do for Go services. So I said signals. I'm not going to favor one signal type to another, but rather focus on how we collect things and why we collect them the way we do. This talk is going to mention a lot of metrics, traces, and profiles, but don't assume that these are the only signal types we care about. So to give you a little bit history, Google is a dominantly distributed systems company. One of the most common architectural patterns we use is the microservices architecture. We have thousands of different microservices built and maintained by hundreds of different teams. And being able to observe our systems is a fundamental reason why Google is reliable, fast, and user-friendly. In order to be able to observe our systems, we obviously need to care about instrumenting our systems. We invented collection and data export, collection and export formats, as well as some philosophies in this area to achieve that in our scale. Our instrumentation stack cares about efficiency and the overhead of the collection. So observability is a core part of our engineering culture, and we enable it by making it easy and also low overhead. Before digging more into the distributed systems observability, I will explain you why it's a little bit more complicated to observe a distributed system. This is a typical architectural diagram for pretty much every product at Google. So we usually have this user-facing, business logic-heavy front-end server that depends on various other services. In this case, you see that like auth, billing, and reporting are those immediate services the front-end server is dependent on. And in this example, all these like relatively low-level services depend on Spanner and eventually hitting the blob store for persistency. In any microsystems architecture, it is expected. Some of the services are becoming a common dependency, like the blob storage or Spanner. When the rest of the company is dependent on blob storage, it is harder for this team to gather meaningful metrics and profiles and so on. It's hard for them to tell the root cause of the problems that is triggered by their users. Blob storage team will see some fluctuations in their dashboards, but may have a hard time actually breaking down the data and figuring out where the problem is originated at. It's also, worth to mention it's not only when the things are obviously going wrong. Infrastructure teams often want answers to be able to just say that things are going right. Some of the example questions they want to ask about their systems are, hey, are we meeting the SLO for the Spanner team as the blob storage team? Are we providing them, a good enough service, the service we promised to serve? Or, what is the impact of this high-level service on the blob storage service? Or what happens if this product grows, 10% overnight? Is the blob storage deployment going to be able to scale? And, what are the next steps for us? This is why we want to be able to break down our signals in various different ways. We call these various different ways dimensions, And with dimensions, you can query the collected data in ways that will help you to answer some of these questions. You can query, for example, you can say, give me the blob storage request latency distribution for RPCs originated at Google Analytics front-end server. Or you can say, give me all these traces and reports that contains this specific RPC. Or give me the CPU profile for this specific library. But only for the RPCs, the cost we have seen observed for RPCs started at Google Analytics. So it's great that that we now can query this data, but how do we actually collect the signals in order to be able to query the data this way and break down the diagnostics data by multiple dimensions? The answer is we record the data with various key value pairs. We call these key value pairs tags at Google. And then the backend, for example, if it's a monitoring backend such as Prometheus, can filter the data by tags. So the entire premise of microservices is, there should be no tight coupling between different services. But then, how can a low-level service such as the blob storage service can tag correctly, if they don't know anything about about its dependents and their, business cases? This is where we get some help from the world of context propagation. So the tags are produced at high-level services such as the Analytics front-end server, and then passed all along to the low-level services as a part of the RPC. You can see that from all the way up to the bottom, you can see the RPCs are tagged. So blob storage actually doesn't know anything, but it records with the incoming tags. So the data we collect at blob store has all these dimensions. So we have a culture of producing tags at the high-level services, depending on specific requirements of the teams, and we propagate these tags all across with RPCs. Then each component in the system can record metrics, profiles, etc. with the incoming tags. As I mentioned in the beginning, we have a holistic approach because each signal type is useful to answer a different question. For example, distributed traces are not able to tell you about CPU hotspots, or CPU samples cannot tell us about the end-to-end latency problems. So we collect various signals, examine the problem from various different perspectives. We shortly realized that it's very hard for our developers to think about all these dimensions, signal types, and build highly efficient instrumentation libraries and instrument each layer they depend on. That's why we built a common framework and decided to open source it lately and make it vendor agnostic so that everybody can use it against any provider. Recently we announced that we are our project Open Census. This is a new holistic instrumentation framework. It's inspired by Google's internal census project. The main reason we are open sourcing this is we want to fill that missing building block in the open source world. We want libraries, frameworks, and all sorts of infrastructure projects to be able to instrument without having to depend on any vendor and without having to reinvent these concepts. So we also want to help other organizations to adopt these solutions because we already have built them, or you can use Open Census as a reference implementation. So Open Census provides a single set of libraries. Currently we have a tag library, metrics, and traces, and we will have more in the future. We have language support for Go, Java, C++ right now. There are more languages are coming, Python, PHP, JavaScript, C# and Erlang are the next. Our libraries are vendor agnostic and can upload data to any backend. We have support for Prometheus, Zipkin, Jaeger, and some APM vendors. And some of the APM vendors actually want to utilize these libraries rather than inventing their own libraries. We provide out-of-the-box instrumentation for some frameworks such as gRPC or common HTTP libraries like NetHTTP package, for example. Also, our libraries provide some introspection and can render a tiny dashboard to report the usage from a single process. Without having to really rely on an actual, external service, you can see what is going on in a single process. It is extremely useful if you know that, the problem is coming from one specific process, or, you can use it during development time. So speaking of framework integrations, I'm going to give a little bit of snippets from our gRPC integration. At Google, we are also responsible for our internal gRPC study observability. So these integrations will be used internally all across at Google too. You need to import our plugin and pass it as a stats handler to the gRPC client and servers. In this case, we're looking at a server, but it's pretty much similar for the clients. And then in the handler, you can extend the incoming tags from the incoming context. In this case, I'm just inserting hello as an originator service and inserting the user ID. So it will be possible to break down all the collected data even at the very low level services by originator and user ID. So this is how you record values. I have a measure here, total hello, that represents the number of times we said hello. Stats record will say 1 with the tags in the current incoming context, so you will be able to tell the number of hellos by originator service and by specific user. Then in your dashboard, it looks like this. You break the you break down the data by dimensions. The baby blue here is representing the total number of hellos from RPCs originated at the auth service. And the purple one is coming from billing, for example. And 2 other colors are representing the other originators. The gRPC plugin also automatically creates traces for incoming and outgoing RPCs, but you can also add custom spans using the trace package. Here we have we are creating a custom child and finishing it. And then, you can create as many spans you want and annotate them. Just propagate the context, and whoever's, starting new spans from that context will be able to trace the existing trace. So here's an example of the, the output, all the traces collected for an RPC. You can see the internal RPCs made in order to satisfy the original incoming request. OpenSenses also provides support for pprof. If you use our tag package, you can collect CPU samples with the tags inside the incoming context, and then you can see, the hotspots for specific, requests, RPCs, and whatever you have put in your tags. This is an RPC, gRPC server I profiled with OpenSenses. We are looking at a typical, visualization from pprof data. You can see the runtime concat strings spend 9.43 seconds for RPCs coming from authentication, and 3.20 seconds for the RPCs coming from the analytics service. So let me focus on some of the core principles we have. One of our goals is to make instrumentation as much as possible without our engineers thinking too much about the cost. That's why we have this separation between instrumentation and collection. Instrumentation is very cheap actually if you don't have to collect. So rather than collecting all the metrics, we defer it user to turn on the collection. The instrumentation bits are always there and have almost have zero impact on the critical path. And then the end user can decide what to collect. This allows libraries to instrument without thinking too much about it, and then they provide their measures, and the end user can enable collection. The collection it requires explicit enabling, but this is also true for disabling. It allows us dynamically enable disable collection in production. For example, imagine a compression library that is instrumented to measure the compressed chunks. Until you are suspicious about this library, you may never need metrics coming from this measure. But when you do, you can dynamically enable it in the production and start receiving metrics. So observing becoming very easy when you have a static list of things to observe, but systems are always surprising you. You cannot really, you cannot predict what you should observe. That's why we encourage a model that you can dynamically expand the collection. We sample expensive and large data, everything that is cheap to collect and aggregatable doesn't have to be sampled. Examples of sample signals are traces, for example, because they are large, profiles because they are expensive. On the other hand, we may aggregate and in efficient ways and produce cheap and small data to avoid sampling. This is what we do for metric collection, for example. So we don't have to sample metrics at all. It is great because then you can see your 19th, 99th percentile. I was repeating that the data size could be a reason why we aggregate or sample data. One of the other things is we want to limit the bandwidth spent on data collection. So for signals that are aggregatable, like metrics, we try to aggregate them inside the process or in an agent living near the process to reduce bandwidth. At Google, we try to use the same instrumentation libraries nowadays to provide, black box instrumentation. For example, a trace started at a load balancer, can be started at a load balancer. Then our engineers can use the same libraries to, add more spans to that trace. Similarly, our microservices framework, gRPC, provides tags and a core set of instrumentation out of the box. So it's easy for our engineers to, to facilitate what is already there and build on top of that, rather than thinking about instrumentation from very scratch. One of the useful tools we have at Google is the introspection pages served from the servers. You can imagine this introspection pages as a small backend that collects and visualizes data. We don't have great CSS right now because distributed systems engineers don't know CSS much, but well, you can contribute. It's a great useful tool to understand what is happening in the process without really depending on a backend. Also, as I mentioned, it's great for development time. You see the traces page here. There's a small dashboard that displays the spans with different names and, just displays the latency distribution. You can see the details for 10 sample traces for each bucket and the errored one. So it gives you some detailed, keep just a small sample in memory and you can get more to understand what is wrong. To summarize, we have a holistic approach. We use multiple signal types. Tags allow us to break down our data by dimension, so each team can produce them and pass them to the low-level services as a part of their RPCs. We instrument our core frameworks and load balancers and service meshes out of the box. Users automatically get a lot of out of the box instrumentation. And then, they can use the same libraries to add fine-grained details, just like the case in the gRPC, server handler where I was creating custom spans. Our, instrumentation library is optimized to be low overhead and low cost. It makes it, easier for libraries and frameworks to instrument without thinking too much about the cost. I can say that, once you adopt these concepts and put them in place, it gives you a good foundation layer. OpenCensus is already available today and is vendor agnostic. We already support Prometheus, Jaeger, Zipkin, and more exporters are coming soon. So I really highly encourage you to take a look and give us feedback and contribute. And that's all. Thank you.